Archiving started.
Okay, so we're good now. I don't know what happened there. Okay, so we were talking about question 1 of the HR diagram, with which was the question, the temperature range for a G-type star is from 5,200 K at the lower end to 5,900 K at the higher end. What would be the values of log T for that temperature range? So we're just going to go log 5,200 for the lower end, which would be 3.72 for the G9 stars, and then log 5,900, which equals 4.47 for the G0 stars. Okay, and then with a table, you would continue the same way. So you fill in the table by, calculating the logarithm of all these temperatures that are given. I should say complete the table. By taking the logs of all the temperatures that are given for the spectral type. Well, let me say spectral type cutoff. Okay, so you're pretty much squared away with that question? Okay, the next questions start with looking at an HR diagram, and you can go to the GPC Astronomy website to look at like an HR diagram where you can toggle between the brightest stars and the dimmest or the nearest stars, actually. But for some people, there seem to be technical difficulties. So what I did is I actually posted slides in the table of contents of this lab showing the brightest stars on one HR diagram and the dimmest stars, the nearest stars, just happen to be the dimmer stars, on the other HR diagram. Now let me see if I can load one of those into the screen here. I'm going to clear this slide, and I'm going to try to import one of them. Let's see, question 2 asks for find the main M equals, so the absolute magnitude of plus 0.5 and type A0 on the diagram. Estimate its temperature. Let me quickly see if I can upload. I'm just going to bring up the HR diagram of the nearest. Yes. Yeah, how can I tell which one is Vega? Okay. Yeah, let me just label. I'm going to use green. So this would be for, I hope the writing is not so big now. I'm going to put it down here because, okay, the stars are there. So this is HR diagram question 2. And, well, the question tells us that Vega...
Hi.
Oh, hi.
Hey, how are you?
Oh, I'm pretty good, thank you.
Good.
Okay, yeah,
Good.
Go ahead.
I have an echo. Can you hear?
Yeah, I can hear you okay. We're just talking
Okay.
about the, yeah, we're just talking about the HR diagram.
Okay.
And
I'm sorry.
that's okay, yeah, we're at question 2 right now. And the question was how to find, which of those dots is Vega, basically. So Vega, I'm going to write that here, has an absolute magnitude of 0.5. So we can start with that. Now the absolute magnitude is given on the vertical axis. And because, high magnitudes go with low energy outputs, that's why the highest numbers are at the bottom. And then when we go up, so we start out with 20 near the bottom, and then 15, 10, 5. So the top line here is actually the 0 line. So I'm just going to put a 0 up here because you can't really read the 0. Okay. Okay, so what we're looking at is a star that is at an absolute magnitude of plus 0.5. So it would be a little bit below our 0 line at the very top. Yeah, let me just make a little circle around the area. Oh, well, so obviously, the stars that we're considering here are well, okay. Oh, I just got rid of my 0. Hang on. Yeah, unfortunately, this is not a word processor, so it's a little bit clumsy. Okay. Let me try this again. Okay, so we're going to look at these stars here, and we want to know which one of those is Vega, because they're close to a magnitude of 0.5. Type that in. Okay, so stars with M about 0.5. So which one of those is Vega? Well, Vega is an A0 type star, so that was also given. Let me make that in maybe in purple. Okay, so Vega's spectral type is A0. Yes, and then we need to look at the table that we have filled in and calculate all our log T's. And A0, yeah, would be close to, since the table gives the minimum surface temperature, so A0 would be at the upper range of that. So it would be, yeah, just 10,000 or a little bit above. And if you take the log of 10,000, then, yeah, that's just about 4. So it would be log of 10,000 K, just about. Yeah, that would be the ballpark. Okay, so, we go to our horizontal axis, which is our log T. Actually, let me write that underneath. That this is equal to 4.0. So it can probably be slightly above that, because 11,000 is the lower cutoff for a B-type star. So we would think that anything up to 10,999 would still be A0. Yes, yeah, so from table 1, you get the cutoff for A0, and, well, 4 directly at 4.0 or 4.1, so we basically have our picks, and I mean, it's okay, so any of these 4, probably any of the 2 that are more to the left, but any of these 4 could potentially be Vega. Actually, no, that's not correct, because the 2 in the overlap zone are going to be Vega. So so any of the 2, of course I'd have to look it up exactly, but it's fine if you go with any of those 2. So any of the 2 stars where the green and purple overlap could be Vega. And you don't really have to like totally identify and say, well, that's it. You simply, all you have to do is for number 2, calculate the log T, and you could put that down as 4.0. And, you know, the temperature would be about 10,000 K because it's an A0 type star. Or you could even go to 10,500 if you wanted to. So I usually accept a range of values there. Oh yeah, Lenita just joined us. We're talking about the HR diagram lab, and we're at the second question now on page 18-6. Okay. Okay, so the answer was, you know, in A0 type, the temperature is about 10,000 K, and the log of that temperature would be 4.0. Okay, are there any more questions about number 2? Okay, let me go ahead and save this slide, and I'm gonna, let me just load it up again. I'm gonna clear the slide and then import that image again. So the next question, otherwise it gets, oh yeah, the next question you, okay, let me import that again. Okay, Connor, hang on, my kid is saying something. Connor, geh in den Keller, okay, Daddy's im Keller. Und ich habe hier meine Session. Oh. Naja, du kannst ihm das selber sagen. Okay. I'm speaking German. I'm trying to raise my kids bilingual. And it has the advantage that not everybody knows what I'm talking about. Okay. So number 3, let me write that in here. HR diagram 3 is about, well, is Vega hotter or cooler? Hotter or cooler, and brighter or fainter than the sun? Okay, well, and the sun is the purple dot that is right here. So let me just point that out. Okay, so here we have the sun. Okay, and we had said that Vega was one of those two up here. Well, let me just pick this one star here and just call this one here. Oops. Let me just undo that and make the circle a little thinner. Okay, let me call this star here Vega. Okay, so this is Vega. Well, so we have to decide two things. Is it hotter or cooler than the sun? Well, what do you think based on where it is in the HR diagram compared to the sun? Yeah, it's definitely hotter because it has a higher temperature log. And then, of course, you know, if you would use 10 to the 4, that would give us 10,000, and the sun, you know, is more around 5,800. Well, yeah, think about that again. So let me just circle the hotter, and yeah, 8, no cap. Chasing our cat. Well, think about it again. Towards the bottom of the HR diagram, where we have the high magnitudes, but they correspond to low luminosities and low energy output. And the higher up you go along the the y-axis, you get to smaller magnitudes, but that corresponds to higher luminosities and higher energy output. You know, so Vega's absolute magnitude is smaller than the sun's, but that means it has a higher energy output. So it is, since we're plotting absolute magnitude, that means it really is brighter than the sun. Okay. Let's see, let me write a couple of comments to that. So hotter because Vega has a higher temperature. So I'm going to write that up here. So because it has a higher temperature and a higher log T, that's why Vega is hotter. And because it has a smaller magnitude, absolute magnitude, that's why it is brighter. Okay, and I'm going to make circles around those. So that would be the reason for this. Okay, my dog just drank out of my glass of water, so I won't be having that anymore. That's better than fighting with the cats, I guess. Okay. Are there any questions about this one? Question 3? Okay. let me clear the slide again. And the next question is, there are 4 white dwarfs on the HR diagram. The faintest of these is Van Maanen star. Estimate its brightness and temperature. Okay, so let me import this image again. And we're still looking at the HR diagram of the nearest star. Okay. Hang on, let me just give my dog something to drink really quick because he has my glass in his mouth. Hang on just a second. 8, 2. Okay, I'm back. Sorry about that. He had a giant fuzz in his water, so he didn't want to drink what he had. Okay. Let's see. Yeah, where's this found again? These HR diagrams, you can either find them on the GPC Astronomy Lab's website, which is a link in the table of contents of the HR Diagram Lab, or I've also posted them as images directly, like the HR diagram of the nearest stars and the HR diagrams of the brightest stars. So I've posted them directly in the learning module for the HR Diagram Lab. Okay, so question 4, we're looking for Van Maanen star, which was supposed to be the faintest of the 4 white dwarfs. So white dwarfs are the hot but very dim stars, so they're usually on the bottom left. Okay, and these are the 4 that look to be, okay. I just tried to circle it and it didn't. Let me try a different color. Okay, that doesn't seem to work either. Let me see if I can type something. So. Okay, so that comes out. Okay, and Van Maanen star is the faintest one. Okay, let's see if this works. Okay. Okay, that's too thick. Okay, something like that. Okay, so Van Maanen is the faintest white dwarf. Okay, and the question is, sorry, just type this up, HR diagram question 4. We want to know if ein Mahnenzahl, well, first of all, we want to know what is roughly its absolute magnitude, log T, and the temperature. So what's the absolute magnitude? What's the log of the temperature? And then finally, what's the temperature? Well, how do we read off, let's see, the absolute magnitude is 16. Yes, that would be pretty good because, yeah, it's below the 15 mark, but since going lower means the numbers are getting higher, yes, so 16 would be a pretty good estimate. Okay, so, yeah, we can say an absolute magnitude of 16, and the log of the temperature, what would be, would we roughly get for that? .9. Yeah, that also looks pretty good, so we can just put in 3.9. And then use that as our exponent to the base 10. So 10 to the 3.9 will give us the temperature. Let's see. Let's see, is that 5,910? Yeah, like I said, I don't have a calculator with log available. So it should be, see, log 3.9 should, no, we don't want to do log 3.9. We want to go 10 to the 3.9 because we want to get, instead of the log T, we want to get the temperature. So basically, let me put that into the chat box. So log T is equal to 3.9. Then, you know, we can get the T by going 10 to the log T, and that's equal to 10 to the 3.9. So it should be, yeah, the 3.9 should be the exponent of the 10. So it should be something just under 10,000 because 10 to the 4 would be a temperature of 10,000. So it's 10 to the 3.9. Yeah, of course, it's not a linear scale, but I mean, it should be less, somewhere a little bit less than 10,000 degrees. Yeah, don't worry about that. Well, maybe I can fill it in later. I don't know if anybody else has a, if you have a TI, like a Texas Instrument calculator, you can just type in, oh, okay, there we go. Yeah, that looks pretty good. Good, 7,000. Yeah, so you just go, well, I don't know if there's even a 10 to the whatever power button. But I mean, you can definitely type it in by hand, 10, and then that little roof thing, and then 3.9, and that should work. Yeah, so see, 7,943, let's just go with that. That sounds pretty good. Yeah, just gotta get it back here. Okay, 7,943 K. So that's our temperature. Okay. We could probably also answer the next question from this slide, because it just asks, is Van Manen star hotter or colder, or brighter and fainter than the sun? I'm just going to put that up here, HR diagram Q5. Well, what do you think? Based on its temperature position, is it on the hotter temperature or colder temperature side of the sun? Yes, definitely hotter, because it's, 7,943 K, and the sun is just 5,800 K, and it's fainter. That's correct. And that's because it is at a, lower on the HR diagram, at higher absolute magnitude. And the magnitude scale was reversed. That's always easy to confuse. So Van Manen star is hotter. And fainter than the sun. Well, I mean, it is a white dwarf, so we would expect it's an exposed core of, a star, of a low-mass star that had just shed its outer layers after the red giant or the red supergiant stage. So, it is an exposed core of a low-mass star, so it should be considerably hotter, but it's incredibly tiny, so that means it's also pretty faint. Okay. I'm going to save this slide. So let's go to question 6. How many of the closest stars are cooler than the sun? Okay, let me load up another version of this diagram. Okay. Okay, in this HR diagram question 6. How many of the nearer stars are cooler than the sun? Okay, so what would you do? Don't want to spend my time counting stars now, but how would you determine that? Yeah, you just count, and, well, which ones do you count? I mean, the nearest stars are all the red ones, but do you count all of the red ones or just certain ones? Yeah, it works out to be everything on the lower right of the sun. If there were any red giants in our solar neighborhood, then those might be higher on the diagram, but they would still be to the right. So in terms of temperature, anything that's colder, you want to count all red dots that are to the right of the sun. I'm just going to write down those instructions here. Count all red dots right of sun. Okay, and I have to abbreviate that a little bit. Okay. So let's save that. Oops. Oh, I'll just clear the slide. Okay, the next question. Of the brightest stars, what fraction are O or B stars? Okay, now I need to bring in the HR diagram of the brightest stars. Okay. So this one is the HR diagram of the brightest stars. All the yellow dots are the brightest stars. You know, and some of the red dots we still see are part of the nearest set, and of course, you know, the sun we also have for reference. And this time we have our log T's across the top. So that's where I put him, because it's basically the top half of the diagram. Okay, so this would be for question 7. And that was, of the brightest stars, what fraction are O or B stars? Okay, well, first of all, how do we determine what are we looking for when we say O or B type star? You know, we want to go back to our table because the stellar types are a temperature sequence, just like our log T is a temperature sequence. So we want to go back to the table where we have calculated all the log T's. So the table was in 18-5, and yeah, so what you would do to complete the table, we talked about that right at the beginning, is you would use the log button, the LOG button, and apply it to the 30,000 to get the log T of the minimum surface temperature of an O-type star. You know, then the log button applied to the 11,000 degrees, you know, to get the log T number for the B-type stars. And well, as a reference point, we had said that log 10,000, if we take the logarithm of 10,000, basically the exponent to the base 10, that would be 10 to the 4. So log T would then be 4. So that's our 10,000 degree line. And any O or B type stars are, you know, above that 4.0 line. So let me just make a line here at the little bit above the 4.0 because we're looking at 11,000. Oh, wait a minute. I wanted a line. Let me switch to the line. Yeah, so that looks pretty straight. So what we have here so the blue straight line stands for the log of 11,000 K, yeah, which is the minimum surface temperature cutoff. So that would be the cutoff for B-type stars. So in order to get, well, first of all, we need the number of the O or B-type stars among the brightest ones. Would you count the stars to the left or to the right of the blue 10,000 or 11,000 K line? So we're looking for the stars, yeah, to the left. We're looking for the stars that are hotter. So we want to count. I'm gonna. Okay, so count the stars to the left. Okay, and you said that's 15. Okay. Now that's just the number. 8, no cat. That's just the number of stars that are type O and B. But the question was asking us for the fraction. So how do we determine the fraction of O or B type stars? Well, fraction means, what part out of the total. So in other words, now we have to count all of them and then divide the 15 by the total number. So I'm going to put that down here. So for the fraction, we want to divide number of O and B, and we want to divide that by the total number. And we're looking at the yellow dots. Those are our brightest stars. The red ones are still part of the nearest set. Okay, so we're going to hang around and count, but basically the 15 stars to the left of the line divided by the total number of all the yellow stars that you see in this image. So that's going to be your fraction. Okay, and then we repeat the same question for the nearest stars. So that's question 8. I'm going to clear the slide. Yeah, decimal is okay for the answer. So you can write it out 15 over whatever number you counted, and you could also express that as a fraction. I think it should be something like maybe a little bit over or under 0.4 or something like that. So yeah, between 0.4 and 0.3, or between 0.45 and 0.35, something like that. Yeah, the decimal would be okay. Let me clear the slide. And now we got to import the nearest ones again. Okay, and on this one, we also want to count the stars that are O and B types. Okay, so this is question 8. Okay, what fraction of the nearest stars is O and B type? Okay, let me put in our 11,000 or log of 11,000 Kelvin number line again. Okay, so again, the blue line is our log of 11,000 K, which is just a little bit greater than the log of 10,000 K, which is 4. Well, of course I should, let me write that a little bit lower, because otherwise we don't even see anything. Oops. I undid one step too much. Yeah, 0. Yeah, that's essentially what we're concluding here, that none of the nearest stars are actually O or B type. Okay, so our fraction again would be and just abbreviate that, number of O and B divided by total number of the red dots. And that happens to be 0. Okay. Save the slide, and the next question is question 9. Which spectral type is the most numerous in the nearest stars? Actually, we can probably put that on the same slide. Yeah, well, maybe not. Let's just do a new one. Okay, so I'm going to import. I don't know if you heard that from the basement, but my husband is watching the Bruins ice hockey game 7 in the first round of the playoffs. So if they win this, they go on. If they lose, they're out. I hope they win, so that my husband is in a good mood. Okay. Yeah, thank you. let's see, of course, what was I going to say? Question 9. Okay, so HR diagram question 9. That's right. What is the most numerous spectral type? Type among the nearest stars. Okay, so how would we estimate that? I mean, the spectral types are, along the x-axis, and it's sort of, vertically. So which log T number do we have around which most of the stars lie? Or which log T line? I mean, if we look at the 4.0, well, yeah, you want to look at the lower right, definitely, and then you want to look at the log T value where most of the stars are clustered around, so to speak. Yeah, let me make a squiggly line around that. Yeah, 3.6 or lower. That would be a pretty good estimate. Yeah, so something like, yeah, this would probably encompass most, or at least half of the stars sort of cluster around 3.5, between 3.6 and 3.4 maybe. So most red dots cluster around log T between 3.6 and maybe 3.4. Okay, so the question now is, what temperature does that correspond to? We can just take the middle of it. Yeah, we can just say, okay, log 3.5. I mean, log T equals to 3.5. So the temperature would be, we can reverse the log by using the number as the exponent to base 10. Okay, so basically, yes, what we want to calculate is 10 to the 3.5 equals, see what kind of temperature? So, okay, so that would be 3,162. Well, yeah, remember the 3,900 is actually the minimum temperature for the K-type stars. So if we get something like 3,162, that's even going to be lower than the minimum K temperature. So 3,162 Kelvin. Yeah, so that would definitely be M-type stars. So those are the most numerous in our solar neighborhood. Okay, and then yeah, we're just going to do question 10, 11, and 12 because then with question 13, I have already prepared slides that explain how to do those questions, and I've posted them. Yeah, I want to see if anybody also has a question about Astronomy 1010. I think there was a student earlier from my 1010 class. Okay, so question 10. The closer a star is to us, the apparent brightness, the brighter it is. Why then are so few of the brightest stars in the nearest group? Yeah, let me just save this and then clear the slide. So HR diagram question 10. Why are so few of the brightest stars in the eighth? Quit it. No cat. Jeepers. No cat. Eighth. No cat. Okay, of course, looking at me, well, no, why not? Okay, so why are so few of the brightest stars in the nearest group? Well, here I want you to think of the analogy kind of like as if you were measuring people's height. So the we measure the stars' brightnesses. So the analogy, stellar brightness, and actually let me say energy output because that's what we're looking at with the HR diagram. Stellar energy output compared to human height. Of course, I wanted to change the color, but it didn't take. So imagine you're, the nearest set would correspond to, the height of the, let's say, first 100 random people in a shopping mall. Whereas the brightest set corresponds to the height of the first 100 athletes Okay, well, please forgive my spelling. Athletes at an NBA, or, the college would work just the same, basketball tournament, or NBA tournament, put it that way. Okay, and that got a little bit cut off. Yeah, this is not a word processor, so I can't scroll up or down, but I can, once I save it and I put it in an image program, I can, put in the bottoms of these letters. Okay, so if you use this analogy, then, well, if you look at the first 100 random people in a shopping mall, is it very likely that you get a lot of the tallest people, you know, that are 7-footers and up? Well, actually, yes, that's one of the reasons. You know, the nearest stars, I'm going to type that into the chat box, are overall pretty faint. You know, they're cool and faint. So kind of like a flashlight. So, you know, the question is, would we be able to see really cool, faint stars from a large distance? Yeah, the answer would be no. You know, they are fading out. So another analogy would be, you know, to look at the stars, you know, flashlights, and look at the brightest stars, yeah, as car, or let's say motorcycle headlights. You know, if you have, you know, like one motorcycle among, you know, 100, let's say flashlights, and you move that group further and further away, yeah, at some point or at some distance, you wouldn't see the flashlights anymore. But you would still see the motorcycle light. A little bit dimmer because it's further away, but you'd still see it. So basically, you know, there are tons of dim flashlight stars, or, you know, there are tons of little pudgy people, or little thin people. But the really tall ones, you know, the 7-footers and above, are really rare. So, you know, if you were just counting a random sample of stars in any given area of space, you'd probably have to count, you know, 1,000 stars, and then you might have 2 or 3 really bright ones in there. You know, the same thing with a shopping mall. You could have an entire shopping mall full of people, you know, only 2 or 3 guys that are 7 foot and higher. So that's sort of the thinking here for this particular question. So let me just, I don't know where I can fit a note on this diagram. Yeah, maybe I can do that in the post-production stage. Okay, let me save this image. Okay, and then question 11, which sample would you say is the least biased? Therefore, which HR diagram is the most representative of typical stars? Okay, let me just clear the slide. Okay, and get HR diagram question 11. Okay, and I meant to switch that to black, but it didn't cooperate. So we'll stay with green. So which diagram represents best the typical stars. So basically here we're looking at, what's the best random sample? Where stars aren't, where stars are not picked based on any one of their properties. Well, you want to think about it's either the brightest or the nearest. How did we pick those samples? See, the brightest sample, we specifically selected, the most luminous stars. And it's kind of like, okay, if you go to a mall and we say we're only measuring those people, or we're only counting those people who are 7 foot and above, and we're disregarding anybody who's shorter. So then we're sort of biased in that we only look at the tallest people. But, if we come in and say, well, let's just measure the height of the first 100 random people, then we're not selecting that group based on any of their properties. We just say, well, those just happen to be the first 100 in this mall. So that's sort of what the nearest sample is. Those happen to be the ones that are close to the sun, but they're not there because of any special property of theirs. So the nearest sample, they're only selected because they are close to the sun. So it's basically a random group. If we assume that the sun is not in any special order, that didn't come out at all. I'm going to add that too in the post-production stage. But that's basically the idea. The nearest stars, well, if we assume that the sun is in no special place, it's sort of in a typical random place in the galaxy, then we would expect to see, okay, the stars that we see around us are nothing special, and, how many bright ones or hot ones there are is sort of like a representation of, what the population at large looks like. And if we go into the mall and we look at the first 100 people, we would get a pretty good close height average, to what the average height of the general population is, even if we were thinking of the general population, being 250 million people. So that's the sort of thinking behind question 11, and actually that leads us directly into question 12. Okay, let's see if I can make black work for me now. So the extension, if we could extrapolate the data on the HR diagram to the entire galaxy, which spectral type of star would one find to be the most numerous in our galaxy? So let me just write that out. Which spectral type would be the most numerous or most common in our galaxy? Okay, that would be my biggest cat, who's complaining that the dog is just a few feet away and looking at him. I don't know if you heard that sound. It's quite the zoo around here. Okay, so this would be the extension from our previous question. You know, we want to look at dogs, cats, kids, and then I also have 2 guinea pigs, and of course I got talked into those by the kids. Like, oh yeah, we take care of them. Uh-huh. So who's been cleaning their cages for a couple of years now? Mm-hmm. That would be me. So if anybody wants 2 guinea pigs, they can't be in the same cage though, because they're both males, and one is totally neurotic and will attack the other one if they're in the same cage. Okay, anyway, we want to look at the nearest sample, because that is a typical cross-section of what most stars are like. So kind of like the first 100 people in the mall. So based on this reasoning, the most common spectral type would be well, what was the most common spectral type on the nearest HR diagram? Which one was the coolest one? Yes, M. Okay. All right, yeah. So much for question 12. And as I said, I've already made slides for question 13 through the end. So why don't you take a look at those and then send me questions about those by email. Yeah, then I guess I just want to know, is anybody here from the 1010 lab? She doesn't look that way. I think the student that was here earlier, she left. I don't know if she's going to return or not. Yeah, technically it would be midnight tomorrow, but I mean, I know, you know, a lot of people are still working on more than one lab. So, I mean, if you can get them to me by the end of the weekend, you know, that would be fine. So I'll also make an announcement to everyone. So you can get them. I'll write that in the chat box here. Say midnight Sunday. And that'll be fine. on a weekend trip with my kids to this Cub Scout pack camping trip. So I don't know, I probably won't have access to a computer there. But we'll probably come back around lunchtime. It's just at Fort Yargo, so that's just near Winder. So we should be back around lunchtime Sunday. Well, actually, considering the time and that my kids have CRCT testing tomorrow, yeah, you're welcome. Let me go ahead and jump off so I can make sure they get tucked into bed. I think they have their science CRCT test tomorrow. That's definitely one that I want them to do well in. Okay, well, yeah, let me stop the archive.